Hi, welcome back to Geology. So today we are going to kind of introduce something really big, which is minerals. And we're going to talk about what kind of makes them up, what are some of their properties. Last time we met, we did talk about the characteristics that make up a mineral, like it's naturally occurring, it has a chemical composition that is always the same throughout. Those types of things we're going to elaborate on a little bit more. And then we're actually going to get into the process of actually even identifying different types of minerals so that you can see some of those properties in a hand sample. So let's go ahead and get started. Make sure you get out a sheet of paper and take some notes today on something that is really important, because we will talk about how minerals justify other things as we move through this earth science units. So first off, just kind of a review. To be a mineral, there are 5 characteristics that have to be present. First is that it has to be naturally occurring within the Earth's crust somewhere, shape, or form, meaning that humans did not make it. It wasn't created due to some type of something being put there, and then over time it changed. This is a naturally occurring element that is being produced, so it's a mineral. It also must be inorganic, meaning that no type of living biotic factors are in it. So no plant, organisms, anything like that are a part of the mineral. It does have to have a crystal's shape or structure to it, and that's what we're going to kind of get into today. What are those different types of crystal structures? Because sometimes you might look at a naturally occurring rock and be like, wow, that crystal looks more like a cube, or there are some that have almost a pyramid look to them. I always think they look kind of like the Washington Monument. So there's a different type of crystal structure that can be present. The atoms must be arranged in a particular type of pattern, and we will discuss what that looks like. And then it clearly must be a solid. So those are the 5 characteristics that kind of make up a mineral being its certain type of characteristics. So kinds of minerals, and so we'll talk about all different types, but technically there's just 2 groups. So minerals are based on chemical composition. Rocks are also then based on the mineral composition, so it kind of, once again, it's a building block of different things. So most common rocks forming minerals are, and you can kind of take a look here. These are minerals that we'll talk about: quartz, orthoclast, plagioclast, muscovite mica, biotite mica, calcite, dolomite, halite, and gypsum. You've seen some of these probably before, you just don't realize it. A lot of these are found in like countertops and stones that are used in your house. Gypsum is normally found in drywall, so if you've ever seen kind of drywall fall apart, there is some gypsum in it. And I know if you've had me before, I've pulled out muscovite and biotite mica. I like to show them. They're very heat resistant, so when we talk about thermodynamics. Quartz is also one that is pretty popular as a gemstone, so you might know someone, or you might own a quartz necklace, ring, earring, something of the sort. And calcite is something used quite a bit. So once again, there are 2 different types of mineral groups, which is our silicate minerals and our non-silicate minerals. And someone that was very not creative came up with these 2 terms, but they actually do have some very, very big properties. Silica is an element that is very abundant in the Earth's crust, and so there are lots and lots and lots of minerals that have the element silica in it. The most common is SiO4, and as you can see, it is made of silicate minerals, normally have silica and oxygen in them. So you will see a lot of these when we look at some of their chemical formulas, and that's why we went over the periodic table. It will have silica and oxygen. Non-silicate minerals clearly do not have silica or oxygen in them. They are not made from the above mineral-based composition, and we'll kind of talk about what those look like here in just a moment. So let's focus in on our silicate minerals, because there's a couple of things that are really important about them. First off is they're the most abundant. 90% of the Earth's minerals are made up of the silica tetrahedron. And that is a big fancy word for a pyramid. So if you take a look at this picture down here, what we have is the Si is the little yellow molecule here, and then it is held together by the 4 oxygen, and that's what it's made of, Si and O, silica and oxygen. So the silicon is surrounded, the silicon is the yellow dot, and then it's surrounded by 4 oxygen, and it forms this pyramid, this tetrahedron shape of material. And once again, this think of triangle. If you've ever had like an engineering class, the triangle is a very strong structure. So if you look at a lot of engineering designs or just buildings in general, you will see that the triangle is a very sturdy structure that can hold things together. So silicate minerals can normally be pretty strong, especially on some sides of it. So we can find silica in glass and sand. Tetra stands for 4. That's where you get the tetrahedron, 4-sided. Hedron is our shape, and then it makes chains of the tetrahedron. So it'll either make a single chain of just like a whole bunch of almost like triangles pointing downwards, or they'll interlock, making a double chain. And I'll show you a picture of that here in a minute. So silicate minerals have a distinct structure, which is called the silicon-oxygen tetrahedron, which is just, once again, this tetrahedron shape right here. And so we get almost like these pointy figures in our silicate minerals. Many different arrangements can be made with the tetrahedrons that result in different bonds. And the bonds can be really, really strong, or they could be really weak, and we can kind of break them apart, just depending on how it is. So the bonds are isolated and ring silicates, rings and double chains, and then sheet silicates and or framework. And what that means is all of this right here. So I'm going to work from below and then get to the more complicated as we move up. So the first one is just, once again, our little tetrahedron. We have our silica in the middle, and then the 4 oxygen, and then we can also have that as, so it's an associated citation, so iron and magnesium and calcium. The most common mineral that we have in class that we'll look at is olivine, which is super pretty. It's this little green pyramid. I have pictures and stuff that we'll look at here when we're in class. It is also a gemstone, so you may have heard of it as peridot. I don't remember what month it is, but it's, once again, this green color. It's actually found quite often by a volcanic activity, very active area where it's been erupted up to the surface. Very, very beautiful. Actually, Hawaii even has green sand beaches, and it's from this olivine being embedded in the sand that gives it its greenish colors. Very pretty. As we move up, we can then have our single chain of tetrahedrons. So they're kind of interlocking a little bit. That's our single chain. And this is an example of pyroxene, which is a common mineral that we'll talk about. It's a little bit darker in color. Getting stronger as we move up here, or another chain that can be pretty strong, is our double chain. So you can see we put 2 of these together. And once again, that makes our double chain, and we can have the common mineral is amphibole, that is there. And then finally, I know none of these make sense, but I promise we'll look at pictures of them here in a little bit. And then finally, the more complicated is our sheet layers. So really strong, pretty strong, strong. This is actually strong one way but weak the other. Muscovite mica and biotite mica are things that we can actually kind of rip apart. So what happens is that these, if we think Fe and Mg, iron and magnesium, these are heavier elements. So these are stronger. And as we kind of move up here, you can get the idea that we've got potassium showing up. And then even up here, too complex to draw, sodium and chloride. And so these are different types of minerals that form under different types of pressures and temperatures, normally in a magma chamber somewhere below the surface of the earth. So somewhere in the asthenosphere, but deep below. And the magma chamber will form some of these heavier elements or heavier minerals first, and then it kind of releases and moves up, and then the other elements form, and it kind of keeps moving up until it reaches the surface a little bit. So non-silicate minerals are the other percent of the earth minerals, and they do not have like a nice shape to them. They are normally formed by some type of deposit or evaporation of liquid, and it's left there. So there are 6 major groups: the carbonates, the halides, the native elements, oxides, sulfates, and sulfides. And so we'll go through and kind of talk about some of these, but to give you an example, halite, which is actually just rock salt almost. If you were to lick halite, it's going to taste like salt. Calcite is another one. It's actually a leftover from evaporites. And then pyrite, fool's gold, and galena, which I have some really big samples of galena that I'll show you. So non-silicate minerals derive a diverse chemical composition, meaning that they can look a little bit differently. They can normally form in cubes, hexagonal, or irregular, and that's what we're going to make with our crystals as we grow some in class. And these are normally ore, meaning that they're mined for use of some way. So if you are a lover of minerals and you go to study them, you would be called a mineralogist. So lots of them become then gemologists, but they are pretty much studying minerals and classifying them. Couple of different things is that as we talk about minerals, there are characteristics and properties in which we will identify them, and so you'll get used to hearing these words here. So there are 7 or 8 of them, so I'm going to kind of go through them here just to kind of give you an idea. One property that when we are observing a mineral, I might ask, well, what's the luster? And that just means how shiny is it, or is it reflecting light? The crystal shape is also another type of property that we will observe. Is it cubed? Is it hexagonal? Does it have that pyramid, tetrahedron type shape to it? Fracture and cleavage is the ability to split along a sheet. So meaning, can I break it apart really easily? Is it fragile, like I can just clunk it apart, but can I like get like pieces of it flicked off into a flat plane? And that's a characteristic of that weak bond between the silicates. Color is actually probably one of the least properties that we want to pay attention to, because minerals can possess many different color properties, but sometimes we do note it down. The one that we'll use the most is what is called a streak. Streak plate. We're going to take the mineral, scrape it across, and then look at the residue that is left on this clay plate. That is going to give us a true color of the mineral and what powder it is. And then that we can relate that streak color back to a grid, which will help us identify the actual mineral itself. Mohs hardness scale. We'll spend a little bit of time looking at that today. So there was a gentleman, his name was Moh, and he was a mineralogist who was observing minerals and realized that they have different hardnesses to them, meaning that some can be really hard and can scrape other objects, and some are really soft that when you take your fingernail, you actually scrape it. So 1 is the softest on Mohs hardness scale, and 7 is the not the most strongest. 10 is the most strongest with a diamond. A diamond is the most strong, but a diamond is not a mineral. So yes, it is. Sorry, I lied. And so soft ones would be like talc, like things that are found in like baby powder. Very, very, very soft. And we'll practice this too. And then 7 is, like I said, kind of in the middle. Crystal shape is extremely important. And then density of a mineral also helps us figure out what mineral it actually might be if we're questioning what we're looking at. So those are the different properties. We can also identify minerals into 2 different categories as metallic and non-metallic. Metallic is just looking at what kind of shininess it has. So sometimes it can have a really big luster to it, like this one, or not so much, which is going to be our non-metallic. And then there's some terms that we use as well. So hopefully this was helpful. We'll get out samples and look at them as we move through the next couple of days. Thanks.